All right, welcome back for another optimization problem. So this one is building a rectangular pen. So I grew up on a farm and we actually did things like this. We had goats and sheep. And it's a rectangular pen with three parallel partitions. And so you might imagine that you want to have, in this case, we'll have four different chambers for maybe different sets of animals. And if you notice, I haven't drawn it in an even way. The problem doesn't say they have to partition the rectangle into even areas, and we'll think about whether or not that matters. And so in this problem, I've drawn a picture, and the question is, what dimensions will maximize the total area? And so, okay, so we want the goal, let's write that down as a goal. We want to maximize area. And in this problem, we're given a constraint that we have 500 feet of fencing. Right, so that's kind of interesting. And so let's get some variables involved. We need to label some things. I like using length and width because I kind of like drawing the L is kind of fun. And if I do that, well, if I look through here, I've got my length and I've got my width. And I also have these little areas in here too, right? So every line segment that I've drawn is now labeled. And if I work out what I have, well, how much total fence do I have? Well, I have 500 feet. And so apparently what that must mean is that 5 L's plus 2 W's must equal 500. Right? I've got 1, 2, 3, 4, 5 of these vertical things, and then 2 of the horizontal widths. And so whatever L and W are, they've got to add up according to this equation. And so our goal is going to be to maximize area. And what is area? Well, area is just going to be length times width. And so our goal is to maximize what L times W would be. And if we wanted to, we could kind of work out a table. For instance, what if L were equal to 50? If L were equal to 50, then we could work out what W would equal, and we could work out the area and test a bunch of different examples. But we're going to try to do that using calculus to see if we can get the answer more efficiently. And so to do this, what we're going to do is we're going to take our top equation, our given equation, and we're going to solve for one variable in terms of the other. So in this case, we're going to solve for W. So I'm going to solve for W is going to be 500 minus 5L divided by 2. And I can simplify this a little bit. So that's going to be 500 over 2 minus 5 over 2L. And I can simplify that even more. That's 250 minus 2.5 times L. So let me move this all here. So I have this nice, beautiful formula for W. The W is going to be 250 minus whatever 2.5 times the length is. And so now I can use that to get my area in terms of just one variable L. So if area is length times width, that's the same as 250 minus 2.5 L times the length, right? Sorry, I think I wrote that in maybe the opposite order than what was above. So it should be length times width, and this thing I'm circling here, that's equal to my width from above. So I'll highlight that maybe in purple. So our width is the same as 250 minus 2.5 L. So now I have my formula for my area. It's going to be 250 L minus 2.5 L squared. I just FOILed that out. And my goal is to find the maximum value of this. And it's probably good to think about what the domain would be. Oops. What the domain of this function would be. Right? So our variable is L. And of course, L can't be negative, right? We can't have a negative length. And if you think about the biggest it could possibly be, well, if you look at this equation up here, 5 times L plus 2W equals 500, well, the biggest L could be would be 100, right? If L were 100, we'd have used up all 500 feet of the fence just in making the parallel bits there. We wouldn't have anything left over for the width, right? And so our domain is going to be that L is between 0 and 100. Okay. And so now we've got a problem. So now it's just a calculus graph problem. We have a function and we have a domain, and our goal is to find the maximum. And so let's do that. So our function is a of L, it's a function of L. And how do we find the maximum of any function? Well, we're just going to do the same steps we always do. So we're going to check the endpoints. So we're going to check L equals 0, L equals 100, just to make sure the maximum doesn't happen for one of those. So if that were the case, well, if L were 0, then our area would be 0. And right, if our pen had length 0, that would not really do anything for us. And similarly, if L were 100, we would also get a value of 0. Right? You can kind of see that here by noticing that the second factor is, of course, going to be the width. And if we use up all the length with our all of the fence with our length, we wouldn't have anything left for the width. Right? So in this case, we know that on the two endpoints, if we were to graph our function, if we were to graph a function a of L, we know if we let L equal 0 or L equal 100, we get a value of 0. And so now we need to check the critical points in the middle to see where the maximum would happen. So critical points are going to be points where the derivative is equal to 0 or where it's undefined. So these are going to be points where a prime of L is equal to 0 or undefined. So let's do that. Let's find the derivative of a. So the derivative of a, we can just use the power rule. So 250 minus 5 times L. And I just use the power rule to find the derivative of 250L. That's just 250. The derivative of 2.5L squared, the 2 comes down. We get 5L. And that's a nice function. And I wanted to know where this is equal to 0 or undefined. Well, it's never going to be undefined. I can always do 250 minus 5 times something. So if I set it equal to 0, I will get then 5L equals 250, L equals 50, and I have found my critical values. This is my critical point. And since I found a critical point, I can now plug in my point into my original area function and see what I get. So if L were 50, let's actually just draw the whole thing. Right? If L were equal to 50, so we'd be using 50 5 times. So we'd be using up 250 of our fence, 250 feet of our fence. And now we've got still 250 left. So I guess this would be 125. And so according to this picture, our area should be 50 times 125, which, let me quickly calculate that and see what I get. 50 times 125, that is 6,250 square feet. Guess I should put units in there. And of course, we would get the same thing if we just plugged it into our formula, right? If I were to just plug in A of L, remember we had a formula for it, 250 length minus 2.5 length squared. If I were to just plug that in to my formula, I would get exactly the same thing. I'm just going to do that now to check, make sure I haven't done any mistakes. But if I plug in 50 into this equation, I'm going to get 250 times 50 minus 2.5 times 50 squared. And I've double checked myself, and I indeed get the same answer. And so now I'm going to finish writing up this problem just to kind of explain what we did. And so because we checked the endpoints and all the critical values, all the critical points, we know the maximum happens at one of these places. So therefore, our maximum happens when L equals 5, width equals 125, and the area is equal to 6,250 square feet. And so typically when you're writing up problems like this, it's always good to write your explanation that justifies why you found a maximum or a minimum value. And I think, I mean, in another video, I'll do one with the maybe first derivative test with the number line. That's something that's possible. But really, if you use this extreme value theorem that we learned in class, it does guarantee that no matter what function you have, the maximum or minimum of that function will always happen either at an endpoint or at the critical points. And so as long as you found all the critical points, this method should work. So this is a great place to stop. I'm aiming to make more of these videos, so stay tuned.